So in 4.5, we're going to talk about derivatives and how that affects the shape of a graph. I have been hinting at some of this stuff throughout our exploration of derivatives. So some of this stuff will be familiar and we'll kind of just know it already. Some of this stuff will be completely brand new. So this is a super important section for us. You may recall when I taught you pre-calc that I would say, we can't really tell the exact shape here because we don't know derivatives yet, or you'll learn that in calculus. So we're going to kind of put everything we know about graphing finely together in this section. So it's just a super important section. So please make sure that you are invested in it because it is important. We're going to start out, we're going to do pieces and parts to it. But one of the most important things that we have already talked about is that if your first derivative is positive, our function will be increasing. So that means the slopes of our tangents are positive. If the slopes of our tangents are negative, then our function is decreasing. We know that already. So really, if we know the first derivative is greater than 0 in that section, our function is increasing. If our derivative is less than 0, our function is decreasing. So that's going to be an important concept as we go through this process. So we want to talk about critical points and derivatives and how they look and what we should expect. If a graph comes to a point, some books will call that point a cusp in the graph. If they come to a point, that cusp like that, one side of our derivative, or if we look at the definition of a derivative, the limit on one side will not match the limit on the other. So at that particular type of point, our derivative is undefined. That happens in an absolute value function. Here at this point, we can see there is a local minimum right here at B, and the first derivative is 0. Here we can see there is this strange thing that happens. It is increasing but keeps increasing. This is a critical point, but it is not a critical point that's anything funny. This is going to be something called a point of inflection we're going to be learning. Here is a critical point. Our first derivative is equal to 0, and we have a local max. And in this particular graph, if we assume it ends here, that would be considered an absolute maximum. Okay, so critical points, remember, critical points tell us not everything about what's happening, but watch. If it is increasing then decreasing, what kind of bump are we going to have? Well, if our first derivative is positive then negative, so if our first derivative goes positive then negative, we should expect a local max. If our first derivative is negative then positive, so it would be decreasing then increasing, we can expect a local min. If our first derivative, look here, on one side it's positive, and the second side it's still positive. So if that doesn't change, we are going to call that a point of inflection. Still a critical point, but when in further investigation, it is not a local max, it is not a local min, it is called a point of inflection. So those critical points, remember, are the points where our first derivative is either equal to 0 or does not exist. But now we're going to start looking on either side of it. On either side of our critical points, what's happening? You may recall last year we did those plus or minus charts. Have we done plus or minus charts this year yet? Anytime, we're going to explore those again and how we can use those to help us pinpoint these things. So here's the first derivative test. If the function is continuous and differentiable on some interval I and C is a critical point. So if it is a critical point that exists, so it exists. So it's not like that cusp or that point. If it goes from positive to negative, if our first derivative changes from positive to negative, we're going to get a local max. So this first one says it would be increasing, then decreasing. It's going to be a local max. This one, it is decreasing, then increasing. It's going to be a local min. If they are the same side on both sides, so if it is increasing, then continues to increase, that's going to be a point of inflection. So now we're going to be exploring what happens around our critical points. Now, if we want to solve a problem using the first derivative test, we are looking at what the graph of a function is doing. We find all critical points that are in our interval. We're going to make a plus or minus chart, and then we have to explore how is the signs changing. And that is going to tell us whether it's a local min, a local max, or an inflection point. Now, there is even a second derivative test, and we're going to explore more even what the next derivative tells us. The first derivative tells us whether it's increasing, decreasing. It also tells us local mins, local extrema, critical points. The second derivative tells us a little more about the curvature of the graph. So in this section, we're exploring what the first derivative gives us and eventually even the second derivative. So remember, your critical points are where the first derivative equals 0 or where the first derivative is undefined. And then we're going to make a plus or minus chart for our function with all the critical points on that plus or minus chart. And then we're going to look at the changes in sign. Okay, so let's look at our first problem. Okay, let's look at our first problem. So it says to use the first derivative test to find local extrema. So for the first time, we're really going to pinpoint where those maxes and mins are. In pre-calculus, I would always say, hey, I don't really know how high the bumps are, so just make a bump there. Well, now we're going to find those bumps. Okay, so what's the first thing you want to do? You want to find all critical points. Well, how do we do that? We need the first derivative. We need to find where the first derivative is equal to 0 or undefined. So we're going to take our first derivative using everything we know about first derivatives, which is 3x squared minus 6x minus 9. Now, that is a polynomial first derivative. It is never undefined, so everything about it works. So we can't find a critical point because there's an undefined point, but we can find a critical point where it's equal to 0. So you're going to set that equal to 0. Now, zeros of a quadratic are found either usually most often by factoring. Yeah. Can you say that one more time? Yeah. So there's two ways you can find a critical point, where the function is undefined and where the function is equal to 0. Since this is a curve that is always defined, it's a polynomial, it's a continuous function, there's nothing here that makes it not work. So we don't have to worry about that portion for a polynomial. Here's where you have to worry about the undefined ones. If it's a fraction, where's the denominator equal to 0? If it's a square root, is there some negatives that make it messed up? So this kind, they're perfect. We just only have to do the 0 portion. So we're going to set that equal to 0. I usually go for the factorization if I can. I notice that everything is divisible by 3. So I get that when I divide everything by 3. And then I can factor it down one more time to get x minus 3 and x plus 1. So my critical points occur where x minus 3 equals 0 and x plus 1 equals 0. Now, if this piece had an x, you would have to be concerned about that. That's a 0. But a 3 is not going to equal 0, so we don't have to worry about it. But don't forget, if you pulled out an x, that does count as one of your critical points. So we have critical points at 3 and negative 1. The second thing we're going to do is we're going to make a plus minus chart for our derivative. Okay? So we're going to put these values on a number line from least to greatest order. Those values exist. They are defined points on our graph. So I'm going to put dots there. If they were an undefined point, I would put an open circle. And I am going to put all of my factors. There's a factor of 3, x minus 3, and x plus 1. Now, the reason I include the 3 is because if that were a negative 3, it would change my chart completely. So I always include every piece and part. Every piece and part. Okay, so I do tend to include it just because. Then I won't forget when an x is there, when a negative is there, whatever the case may be. So a 3 is positive no matter what. So again, if that was like a negative 3, that would be important because that negative would switch things. So I always just include any number like that. Okay, so remember how we did this in the past. We're going to find some test values in the region on the number line. So I need maybe -2, 0, and 4 are good test values. There are millions of test values. Just pick a number in that region so that we can plug it in. If we plug it -2 into those values, we get a positive. Negative 2 minus 3 is a negative. Negative 2 plus 1 is a negative. We have a positive and two negatives multiplied together. That's going to be a positive solution. Now let's do the same thing. Let's plug in 0. Always positive. 0 minus 3 is a negative. 0 plus 1 is a positive. Here we have just one negative multiplied with other positives, so that would be a negative result. Now let's plug 4 into those. Obviously, we have a positive when we do that. 4 minus 3 is a positive. 4 plus 1 is a positive. 3 positives multiplied together is a positive result. So what the heck does this mean? Yes. So here I'm plugging negative 2 into all of those. And in this region, I'm plugging 0 in. And this region, I plugged 4 in. Anything past 3 will work. So I just decided to plug in 4. And then that's a positive because it's positive. 4 minus 3 is a positive. 4 plus 1 is 5, a positive. So we got all positives make a positive. Okay. So let's take a look at what this means. So there's a few different things when we analyze the results that you want to tell me. First, you need to tell me where it's increasing and decreasing. Increasing are all of the intervals where we see positive. Now, increasing and decreasing do not include the endpoints, so we always use parentheses. So it is increasing where we got positive results, from negative infinity up to negative 1, and then from 3 to infinity. Decreasing is where we got negative results, which is in here. Again, increasing and decreasing, never use brackets, use parentheses, because those changeover points are doing something completely different. So it's from negative 1 to 3. So I'm going to make just a extremely rough sketch of what happened, okay? I am going uphill. I hit negative 1 and then I go downhill. I hit 3 and I go uphill. So that is a very rough sketch of what happens. When I go from a plus to a minus, so at this negative 1, it has to be, when x equals negative 1, that is a local maximum. It is a hilltop because I went from increasing to decreasing, okay? Now, here we're going downhill until we hit 3, and then we go uphill again. If we go from negative to positive, so at x equals 3, we must be at a local minimum. So every place that we are positive, that interval is an increasing interval. Every place that we find negatives, we are at a decreasing interval. If it goes from plus to minus, that has to be a local maximum. If it goes from minus to plus, it has to be a local minimum. If it doesn't change, it's what's called an inflection point. But we have to verify that with something called the second derivative test. But, okay. Let's check our work. Can you read to me what the equation was? The original, not function, not the derivative, but the original. Is that correct? Did I type it incorrectly? Okay, so let's look at what happens. What happened at -1? At -1, we have a local maximum. Now, I didn't tell you what it was. You would have to plug it back into the original function. But at -1, we have a local maximum. What happened at 3? There's a local minimum. So this is telling us so much about the shape of the graph. What's happening for the graph? It is increasing until we hit an x value of -1. Then it's decreasing until an x value of 3. Then it is increasing again. So all of the things that the first derivative tells us have come to pass. So that's how you could check your work in Desmos. It should line up with what we found in that plus or minus chart. Okay? Okay. Are everybody good with what we found for that one? Okay. So now let's do it again with a slightly harder type of problem. Let's take a look at example 418. Your algebra skills are really going to come into play because we're going to need to find where does it not exist, where is it equal to 0. Solving those things are going to be a thing. Okay, so first thing we find are the critical points. How do we do that? Well, we need the first derivative. So our first derivative is 5/3 x to the -2/3 minus 5/3 x to the 2/3. And I believe we should be okay there. Yeah, okay. So where the heck, that's a weird problem. So we're looking at where is that undefined and where is that equal to 0. So first, let's just think about the equal to 0 part, because it will kind of reveal the other parts as well. We can take out a 5/3. We can divide through by 5/3 or multiply everything by 3/5. The 5/3 does nothing. It should be on our chart, our plus minus chart. But as far as solving that equation, okay. Let's think about for just a moment. This is really 1 over x to the 2/3. That negative indicates it's actually a fraction. What are we never allowed to have in the denominator of our fraction? 0. So that tells us that this gives us a critical point where that denominator equals 0 would be a critical point. That would be an undefined value. Well, that's just 0. So 0 is a critical point only because it causes a denominator to be 0, which is yucky. So 0 is a problem. 0 is a critical point that we will have to explore. Does 0 work in the original function? Could you plug 0 into that original function? Yeah, you can. You can take 0 to the 1/3 power, 0. 0 to 5/3 power, 0. The only thing you can't take 0 to is a negative power because you can't put it in a denominator. Okay. So now let's just solve that. So I'm going to take 5/3 and multiply by its reciprocal. I am going to now just focus on this part. And I am going to multiply everything through by that denominator so it'll pop it to the top. I've always told you to solve an equation with a fraction in it, you can always multiply through by the common denominator and then you don't have fractions to worry about. Same thing holds true for this type. So if I were to solve this, I would get 1 minus x to the 4/3 equals 0. And that's not a hard equation to solve. Let's take and move the x's away. And then what's going to get rid of 4/3 power? A 3/4 power. What is 1 to any power? 1. So now we found the critical points. Our critical points are at 0 and at 1. What's the next phase we do? Plus minus chart. Okay, plus minus chart. So we're going to go, that's positive 1, isn't it? Okay, wait a second. How about if we put them in order, 0 and 1? Now, let's keep them open circles. I'm sorry, let's keep them closed circles because both of those points do work back in the original. So we really concern, are they a point on the graph? They are both points on the original graph. Okay. I am not going to break this apart any more than right there. We could even use just the original version because it's so disgusting. But I'm going to break up the 5/3 because it's always positive, and then I don't have to worry about it. And I'm just going to plug into 1 over x to the 2/3 minus x to the 2/3. Okay. So what are good things to take a third power of? 1, -1. 8, -8. Okay. So keep that in mind. Let's plug in -1 because that's going to work okay. Let's plug in between 0 and 1 is 1/8. That should work. And then let's plug in 8. I'm just thinking, what is something I can take a third power of? I don't know if this is going to work, but it probably should work. Okay. If you plug -1 in, you're going to square it. It becomes a 1. Then cube root it. It becomes a 1. 1 over 1 is 1. And then square it. Just a minute. -1 is an issue. Go back here. Go back here. You know when you inflict a square root on a problem, you have to include the plus or minus symbol. See how this bottom is even? Guess what we have to have on there? We have to have a plus or minus, yeah. So I'm sorry, that's a plus or minus. I'm like, wait, I got a 0 there. That's a critical point. Anyway, how about if we fix our chart then? Told you this problem was disgusting. Let's put -1 on there. Ooh, so okay, so then we got to plug in -1/8 and -8. Oh, yucky doodle. Okay. So let's plug in 1/8. I was liking plugging in 1 or -1. Okay. So 1/8 squared is 1/64. The cube root of that is 1/8. Flip it, get 8. That's 8. 1/8 squared is 1/64. Take that's 1/8 minus 8. Okay, that's a positive. Same thing's going to happen for here. That's a positive. Now let's plug in 8. I think we're going to get negatives there. Okay, so that would be 1 over 1 over 64, the cube root of that. I'm sorry, guys. It's hurting my brain today a little bit. Is 4. So that's 1/4 minus 4, which is a negative. And then this would be the same thing. That's a negative. Okay. So after that beautiful, lovely. Okay. So look what happens here. we are decreasing, then we are increasing, then we keep increasing. Ooh. Okay, let's try again. We are negative, so we are decreasing and then increasing. We have some funky spot, and then we keep increasing, then we decrease. So this one here is a local minimum. Negative to positive, local minimum. This one here is a point of inflection, most likely. It didn't change. It's increasing through that point. And then this one here, it went from increasing to decreasing. That's a local max. Okay, so now the third thing we have to do is analyze our results. Okay, so where is it increasing? Every place that it's positive, 0 is a point that works in our original, so you can just do that section there from -1 to +1. So from -1 to +1, it is increasing. It is decreasing over here and over here. So from -infinity to -1, and from 1 to infinity. There is a local max when x equals 1. There's a local min when x equals -1. There is a probable point of inflection when x equals 0. We have analyzed the results. Now, this is the last one we're going to do today because we're going to pick a few problems out of the homework that I want you to do tonight and in class, probably just 2 of them. But I would like to put this into a graphing calculator. So let's go over to Desmos and let's put that in. And let's see what we get. Okay, that is so not what we got. Much better. Okay. Oh my goodness, look. At -1, we have a local minimum. At +1, we have a local maximum. At 0, we had a funky spot. At 0, we had a funky spot. Yeah, the tangent line there is a vertical tangent line, and that's what caused that issue. But we're going to explore how the curvature changes right there as we go. We're going to eventually do a second derivative test. Okay. Okay. So going back to the homework, at this time we're going to stop there, and all that I want you to do for today, let's do just 1 through 4. We're going to call it 4-5A homework. Numbers 1 through 4. It is due, 1 through 4 are due by the time I see you tomorrow. 4 problems. Due by the time I see you tomorrow. So let's use some of our time right now wisely. 1 through 4, 4-5A, yes.